Hello, this is Miraj Patel here, and this is the second video in the energy section, and today we're going to talk about how to solve energy problems. And so, before we solve any problems, I'm going to go over the general form of solving problems. Um, it's slightly different from how to solve kinematics. And in kinematics, we used a method where we pretty much stated what we had given, and we listed what we needed, and we picked the formula and solved. But energy problems are a little different. Energy problems are mostly all like basically the same principle, and so here we are going to talk about it. And so the great thing about energy, first of all, is that we do not need to know the path the object takes. So, for example, in kinematics, we had to know that there was constant acceleration, or we had to know it's in free fall, it's falling straight down, it's going in a straight line. But in energy, it can go in all sorts of different shapes, like curves. Uh, it can go up and down a hill. It can go down a ramp. In energy, we do not need to know the path. So that's the great thing about energy. Unlike in kinematics, we need to know it has a constant acceleration. And usually we use the conservation of energy principle in pretty much every problem. In a given problem, we have to identify the types of energy at the end and beginning. So we have three choices: kinetic energy, gravitational potential energy, and potential energy in a spring. So we have to figure out the types of energy at the beginning and end, add the energies at the beginning, and add the energies at the end, sorry. And usually if it conserves energy, or if there's no friction, or it's everything's conserved, then we set both of them equal to each other. If they're not, then we have to do some other stuff, but most of the time the energy at the begin and end are going to be the same, so we just set them equal to each other. And then we have to find out what we need to solve for. So usually you will solve for velocity or height, usually, or you can solve for how far a spring is compressed. So usually, like for example, if you have a ball on a hill and it rolls down the hill, we can figure out the velocity if we know the height the ball was at and stuff like that. So you basically use kinetic energy to find velocity, height from gravitational potential, and distance a spring compressed from potential energy of a spring. So those are like usually what you solve for. So here, let's do an example to show what I mean by the process. A ball is 45 meters above the ground on a hill. How fast will it roll when it reaches the ground? Okay, so picture a hill and a ball on top. And so basically the ball rolls down, and we want to figure out how fast it is traveling at the bottom of the hill. So if you were thinking kinematics, you would not want to use that, because we do not technically have free fall, because it's on a curve or it's going down a hill, the acceleration changes because different parts of the hill have different steepnesses, and so at the bottom it might accelerate less than the top. So we cannot use kinematics. So anytime you have like a ball rolling down a hill, or they give you like the height of a ball and they don't tell you it's constant acceleration, or you don't know it's in free fall, then you have to use energy. So do not use kinematics. So we first have to list the energies at the beginning and at the end. So think about it. At the beginning, the ball's at rest, and we basically let the ball go, and it rolls down the hill. So at the beginning, the ball is just sitting there, and there's no spring, and it's not moving. So it only has gravitational potential. At the end, it's rolling down the hill. So let's just assume the ground is the bottom. So technically, by if we our frame of reference, we call the ground the bottom. So at the bottom has no potential energy, no potential gravitational. There's no spring, so you can rule out that it only has kinetic. So we have potential energy at the beginning and kinetic at the end. And so so basically, we have to assume no friction to use conservation of energy. So in most problems, you're going to have to assume that there's no friction. And if you're taking AP Physics 1, the writers assume no friction most of the time, unless they tell you that there's friction. It is safe to say that to assume no friction. Although ideally there is friction, but for this case and for most problems, assume there's no friction. So we set the initial energy and final energy equal to each other. So I said that the initial energy was gravitational potential at the top of the hill. So we're 45 meters up. We have potential energy due to gravity. Then it gets converted all to kinetic energy as it rolls to the bottom. So mgh, gravitational potential, equals 1/2 mv squared, which is the kinetic energy. So if we solve for v, we multiply both sides by 2, hence the 2, and we take a square root, but since both sides have an m, we can cancel that out. So basically the velocity is equal to the square root of 2gh. So then we plug in what we have. Gravity's -10, height is 45, and multiply that by 2 and take a square root. And we have to ignore the negative sign because energy can only be positive. So even though there's a negative in the equation, in the formula, in the radical, we have to ignore the negative due to gravity. So just take out the negative and you will get the answer. And it equals 30 meters per second squared. And it's important because that turns out to be exactly the same if you use kinematics. But because this is technically not constant acceleration, you shouldn't use kinematics, although it is the same answer. Here is a second problem we're gonna do, which includes potential energy of a spring. So a 1 kilogram box is moving 10 meters per second, collides with a spring. And how far does the spring compress if K equals 15 Newton divided per meter? So we're going to use conservation of energy again because in the problem it says the block is moving on a frictionless surface and the spring is ideal, meaning that it does not lose any energy. Because normally in real life, springs, when they compress and contract, they make a lot of heat from the deformation of the spring. So this is an ideal spring, so it doesn't do that. So again, we have to figure out what energy is at the beginning. So at the beginning, the box is moving and it's on the ground. So let's assume the ground is the bottom of, or is the earth. So there's only kinetic energy because the box is on the earth. Initially the box has nothing to do with the spring, so it's only moving. So only kinetic energy at the beginning, and then at the end the box is the box is stopped and the spring is fully compressed as far as it can go. As far as it can go. Sorry about that. So the box stopped moving, the spring is compressed, and the box is still on the ground. So box stopped moving, no kinetic, no potential because it's on the ground. It's only potential energy of a spring. So those are your two types of energies. So using conservation of energy, initial energy equals final energy. Initial is kinetic energy, final is potential of a spring. 1/2 mv squared kinetic energy equals 1/2 kx squared. And we want to solve for how far it's compressed. So that is x here. So we can cancel out the 1/2 by multiplying each side by 2. Divide each side by k, and then take the square root. So basically we get mv squared over k, and then the square root of that equals x, which is the distance compressed. And so if we plug in our numbers, k, the spring constant's 15, so 15 goes in the denominator, and then 10 is the mass of the, is the velocity, and then the box weighs 1 kilogram. And so if we plug that in, we will get approximately 2.58 meters. So this spring, when this box collides into it, it will compress 2.58 meters. So this spring is really, really weak. So this box really pushes that spring far in. So basically, the kinetic energy in the box, it's converted to the energy into the spring, so potential energy in the spring. So this is the type of problem that most of them will be. So one type of energy converts fully into another form. So this is another typical problem you'll get, just like a ball rolling down a hill, or a roller coaster starts at the top of the peak and then converts to kinetic energy at the bottom and then goes back up. So these are typical problems where one energy gets fully converted to another form. But there's other types of problems where it's not fully converted, and I have one of those after this one. So here is a cool problem that is really challenging and difficult. This is actually from a practice AP exam that I was taking. This problem is really tricky, but it is all has to do with the same type of principle, the conservation of energy. So two people are running at velocity v at a rope hung to the wall. Actually, it should be hung to the ceiling. Sorry about that. One weighs mass m and the other weighs 2m. Which one of them will go higher when they swing up the rope? So this is the picture that you should be picturing in your head. So two people are running at two ropes. So they're both running with the same velocity. This one weighs mass m, and then the other person weighs double. So which one of them will swing up higher? So approach this like any other problem. So just think about it as two separate problems. So the first person and the second person. So think of it as two different problems. They both start with kinetic energy since they're running, right? So they're moving with velocity. They're on the ground. There's no spring, so no kinetic. No gravitational potential and no spring potential. And so the initial energy is kinetic, and then it all is transferred to potential of gravity, because if you swing upward at the at the top of the motion of the swing, you will stop and then you'll swing back down. So we're trying to figure out the height at the very top of that motion. So you're not moving at the top, there's no spring, so there's only gravitational potential. So basically initial energy equals final energy, and kinetic energy is always transferred to potential energy. So 1/2 mv squared equals mgh. And in situation 1, the velocity, or in situation 1, the person weighs m. So we don't change anything except we plug in g. And if we solve for h, we basically just move 10m to the other side, divide 1/2 mv squared by 10m. And if we simplify by canceling out the m's, we'll get 1/2 v squared over 10 equals h. So so this is the formula for the height based off of this problem. Situation 2, the only thing that changed is the 2m. So basically, if we cancel out the 2m's here, we'll just have 1/2 v squared over 10 equals h again, because the masses always cancel out. So just from solving this, you see that there's no mass involved because mass is on both sides. And the same thing happened here because mass cancels out in both kinetic and potential. So since mass was included in both kinetic and gravitational potential energy, it has no effect on the height the person goes. So the people running into this rope here, since mass is in both kinetic and potential energy, they will go the same height because it only matters about how fast they're moving. And it makes sense because if something weighs more, they will definitely have more kinetic energy, and it also they have more gravitational potential energy. So this is a trick question because you would think that the heavier person will go faster or go higher because they have more energy. But since mass cancels out in both the formulas for gravitational potential and kinetic, they will both go the same height because they're moving the same speed. So this is a tricky AP question. So these are the kind of questions AP likes to throw at students. So now we're going to talk about the problem I said that what if energy isn't conserved? Then you have to include work on in your problem. So remember, as I said earlier, a change in energy means work was done to the system of focus. So in the first PowerPoint about energy, I talked about how work is a change of energy. So whenever there's work involved, we have to add or subtract something to the energy. And so you do the same thing. We have to sum the energies on the final and initial conditions, but you must add or subtract on one of the sides because work was done. So there could have been energy added or taken away from our system. So keywords signifying work include friction, some description of a push or pull, or any other extraneous force. So like, for example, if we have a cart and it's moving, then someone pushes on the cart and it ends with a higher velocity, that was work because there was a force and it started moving faster, or something stopped. Like, friction is a great indicator of work. So whenever you see friction, you're gonna have to do something like this. If our system does work on an outside object, we lose energy. If work is done on our system, energy is gained. So this is important. You need to know this. So work, if it's done to something, then if work is done on our system, that means we gain energy. If our system does work on something else, we lost energy, or we lose energy and we transfer it to something else. So it's important we know this. And so here is my problem. So a 5 kilogram ball rolls 20 meters above the ground, and it rolls down a frictionless hill, but it rolls into or onto a rough surface. How far will it roll if the frictional force is 10 newtons? So here we have a ball. It's 20 meters high, and it rolls down this ramp, but then it gets into this red zone, which is rough. So it's eventually going to stop. So basically, we have to think about energy, but in this time, instead of conserving energy, we lose it to work in friction. So we initially start out with potential energy from gravity, and that's because it's not moving at the top and it's just sitting there. There's no spring, and we end up with no energy. So initial energy, we have to first think, is mgh. Mass is 5, height is 20, and then gravity is of course 10. So if we do this, we get 1,000 joules. So we have 1,000 joules of energy. All of this is dissipated by friction. So basically, the friction takes away all the energy. So we can think of it as we're losing energy, so subtraction. So think about subtraction. So we're going to have to subtract something from our 1,000 joules. So if we think about it, 1,000 joules is initial, plus the friction, so the force of friction, equals 0. So basically, the friction is going to take away energy. And the reason why is because friction is exactly 180 degrees to the motion of the ball. It's the theta is going to be 180 degrees. So, and basically, this is going to turn to a negative sign. So, 1,000 minus FD cosine theta, or minus force times distance, equals 0, because cosine of 180 is actually just -1. So basically 1,000 minus force times distance equals 0. And if we plug this into our equation here and solve for d here, d equals -1,000. Imagine moving 1,000 to the other side and then dividing it by d cosine theta. And so I told you cosine of 180 is actually just -1. And so basically 1,000 divided by 10, and they're both negative, so it gives you 100 meters. So basically the friction took away energy, and it just basically stopped the ball, but we just needed the friction. We needed to know how much it had to travel before it did 1,000 joules of work on the ball. So basically, we had the initial energy, but instead we had the friction on the ball, and it did, at the end we had 0 joules because the ball stopped. So here's problem 2. If a skateboarder is on a 15-meter half pipe and reaches the bottom at 15 meters per second, how much energy was lost? So initial energy, the skateboarder is at the top of the half pipe, and let's assume that they're not moving. And so the initial energy is potential energy of gravity. Final energy is all kinetic energy. Let's assume the bottom of the half pipe is the Earth. So once you're on Earth, there's no more potential energy because you cannot fall. So final energy is kinetic energy, and this is we know energy was lost because I told you that at the bottom we have 15 meters per second, and I want to know how much energy was lost. So there had to be friction involved in this because it could have gone faster. So I gave you a height and I gave you a speed at the bottom, and we want to know how much energy was lost because the skateboard could have gone faster if it was frictionless. So there had to be friction involved. So basically, we had an initial energy, and friction slows him down. So it takes away from the initial energy, and if we subtract the initial work from the initial energy, we get the final speed or kinetic energy. So initial energy minus the friction, or the energy taken away, equals the final energy. And so if we solve for friction, initial energy minus final equals the friction. So using our pretty much we use conservation of energy but included work. So it's not really conservation of energy, but it sort of is. And we solved for the work or the friction. And so it's basically the initial energy minus final equals friction. So initial energy was just the initial energy was just gravity, and then we subtract the kinetic energy, and if we cancel out the m's here, we don't really need to know the mass. That's why the mass wasn't given. And so GH 15 times 10 minus 1/2 v squared equals so 150 minus 112.5. It gives us 37.5 joules. So that is how much energy was lost. So another important thing about energy is we can calculate efficiency. So let's go ahead and calculate the efficiency. And I'm sure most of you heard of efficiency. Efficiency is basically how much energy was like kept or transferred without being lost. So how much energy was actually transferred to the final energy usable form. So the formula for efficiency is final energy over the initial energy times 100. So the final energy was 112.5 and the initial was 150. So, and if we multiply that by 100, we get a 75% efficiency. So in real life, 75% is actually a pretty good amount of efficiency. So, and efficiency, it's important to know, can never be more than 100. The most it can ever be is 100, because you can never end with more energy than you had if there's nothing adding to it. So it's important. Efficiency is usually never 100%. I mean, it can be if it's ideal, but in real life, theoretically, you cannot be 100% efficient. And it's always impossible to be over 100. So you can never have efficiency over 1 or 100%. And so last thing about energy is power. So power is the rate at which work is done. So basically, any rate has time in it. So basically, work divided by time will give you power. And power just means, if you have a lot of power, that means you can do work very fast. And so work equals force times distance. And if we do force times distance over time, this is power. And power, it can also be force times velocity. So if we have like an object moving, you can just do the force it takes to keep it moving times the velocity it's moving at, and you get power. So these are two ways to calculate power: FD over time, or force times velocity. And power is measured in watts, which is 1 joule per second. So it's like moving 100 grams 1 meter in a second. So that is about what a watt is. So watt is a pretty small amount of power. And most people, when you think of power, you think of light bulbs, and light bulbs actually measure, their power in watts. And we'll learn about that at the end of these physics videos when we talk about electricity. So here is a simple problem. So what is the power if a person pushes with a force of pushes a box with 100 newtons moving at 3 meters per second? So I basically told you power is force times velocity. So in this case, 100 newtons is a force, velocity is 3 meters per second. So we just multiply that, we get 300 watts. Okay, so here's a little bit more involved problem, but still pretty simple. A person weighing 300 kgs climbs a ladder in 2-meter ladder in 2 seconds. So let's just say the person has no energy at the beginning. At the end, the person ends it. They gain a gravitational potential energy by climbing the ladder. So the gravitational potential energy, mgh, mass, gravity, height. So mass is 100, gravity is 10, h is 2 meters. So that is 3,000. Actually, that should be 2,000 joules. Sorry. So it's 2,000 joules, and that's the energy that they gained. And they did that in 2 seconds. So if we divide by the time, so 2,000 divided by 2, again, sorry, that should be a 2,000. So that should be 1,000 watts. So that is a lot of energy. And for those of you that know about horsepower, 1 horsepower is 745 watts. So if we want to convert this to horsepower, it's 1,000 divided by 745. So this person used 1.34 horsepower when they climbed this ladder, 2 meters in 2 seconds. So this is quite a lot of horsepower. And usually in physics, we don't really talk much about horsepower, but this is interesting how you can relate it to like stuff you might be more familiar with. So thank you for listening to my physics video today. Today we talked about energy problems, efficiency, and power. And the basic fundamental thing about energy is you have to sum the initial, sum the end, and most of the time you set them equal to each other, but if there's work involved, you have to add or subtract to either one and solve for the piece of information you need. The great thing about energy is that we do not need to know the path the object travels. So the object could be on a curve, it could be on a ramp, it could be on a roller coaster moving in all sorts of curves and stuff. We do not need to know the path. We just need to know the end and beginning positions. And the next video, we're going to talk about momentum. And so if you have any questions, or if you enjoyed this video, first of all, please tell your friends and tell other people who's taking physics. And please like the video below. If you have any questions about energy, about kinematics, anything you're learning in fundamental physics, please email me at mpatelbuccaneer@gmail.com. And for practice problems on energy, please visit OpenStax Physics. You can Google that on the internet and it'll show up a online textbook. And this textbook is what I used in my physics class, and it has tons of problems on all sorts of stuff. Usually, like the first 10 chapters are about like introductory physics, what we learned in AP Physics 1, there's like tons more stuff, thermodynamics, fluid mechanics, all sorts of complicated stuff you can maybe read about if you're interested. And for chemistry tutorials, please visit my website, buccaneerchemistry.weebly.com. I hope you enjoy this video. Have a good day, and I hope to see you next time.